So, good morning everyone. My name is Rafal Wojtczuk. I work for a company named Bromium, and the talk is titled Lessons Learned from 8 Years of Breaking Hypervisors. So maybe to start, some word of explanation or justification about the title and introduction at the same time. I've been fascinated by topic of hypervisor security for a long time. The first vulnerability that I have found in virtualization software was in 2006, so ages ago. And since then, I found a couple of other vulnerabilities in different hypervisors, as well as a number of issues in other low-level technologies. So there's a chance I know what I'm talking about, and you're not wasting your time here. Okay, agenda for this talk, about the speaker we're done. We'll talk about different types of hypervisors, and particularly what will be covered in this talk. Then we'll talk about attack surface of the most commonly spotted hypervisors. And not to make it very dry, I will try to show you a couple of examples, real examples of real past and present vulnerabilities. And some of them can be mitigated in a generic way, right? So we'll conclude with a couple of examples of mitigation techniques. Okay, so types of hypervisors. There are many of them. I guess most of you are familiar with products like VMware, Xen, or Microsoft Hyper-V. So the mainstream popular commercial ones running on x86 platform with the purpose of running Microsoft OS VMs, right? And the talk is about them because, again, that's the thing that's mostly popular. But beware, there are other types of hypervisors, particularly in the embedded world. It looks a bit different. Academic projects are sometimes interesting, especially if they are created with the goal of building some secure software. But the problem with academic projects is that they usually die when the grant time's off. They usually produce only some sort of POC that is not usable for real deployment. And finally, one technique worth mentioning is formal software verification, right? So it's very good if we can prove, via mathematical proof, that the software is secure, that it behaves as we would like it to be. So why we should all use formally verified software, right? It's a very good thing to have. Yes, it is. The problem is that formal verification is insanely expensive, right? It's very difficult, requires high-level expertise, and if you change your software a little bit, sometimes you have to restructure the whole proof. So that's the reason why this technology of formal verification is not used very widely, right? And you might have heard that, for instance, SEL4 is formally verified hypervisor. Yay! Excellent. But we'll see that's not the whole story. Okay, the types of hypervisors. Usually there are two broad categories, namely type 1 and type 2. And the difference is that type 1 has the sole control of the platform, right? It starts as the first thing started by the BIOS. And in case of type 2, the hypervisor coexists with the operating system, right? It's important because it's not the only privileged code on the platform. It runs in ring 0 as a kernel driver, but again, it coexists with other operating systems like Windows or Linux. But interestingly, so they are quite different, and it creates a lot of issues, but from the perspective of an attacker who tries to break out of VM, and that's the scenario that we will be most interested, they're almost identical. There's not much difference. So I will just bundle them in a single category, and most of the talk that follows is about either type 1 or type 2. There is another category, and it's DeepSafe. It's a product from McAfee, and it's very different, very special, very interesting, and we'll cover it separately. But for now, let's just focus on type 1 and type 2. Okay, so attack surface. So this is the important slide, right? We just try to understand what components of the virtualization system are most prone to attacks, to put it this way. Okay, so the first line of the defense is CPU itself, right? So in order to have good feasible way to virtualize Intel CPU, you need these VTX extensions, right? That allows you to run code within the VTX container in a VM, right? And of course, we need these instructions to behave properly, right? If some code runs in a VM protected by VTX, but if it could access memory outside of the VM, like it could directly access the memory of hypervisor, it would make no sense, right? There would be no protection. Similarly, if any bit of state leaks from the VM to the outside world after you exit from the VM, and then if you could use it to influence the behavior of the hypervisor, then again, there is no hope. And the answer is this technology works well, right? Throughout all the history since it was introduced, there was no significant issues with that. To be honest and say the whole story, there are a couple of interesting CPU erratas related to the VTX technology, which should not happen, right? We would like the CPU to be totally perfect, but they are not very scary. There hasn't been a single case that I am aware of that you could use the CPU errata to actually break out from the VM and get code execution outside of the VM. They are a bit scary, but again, that's not the main problem. Again, this separation implemented by the CPU, by VTX, is very good, right? And that is why a lot of people think that, again, because the CPU implemented separation is good, that hypervisors are secure by definition, right? And that's totally wrong line of reasoning. The problem is that, okay, this separation is really good, but in order for the VM to be useful, you have to actually drill holes in this container, right? We need to let VM communicate with the outside world to be useful, to exchange information, do anything useful, right? And that's where the majority of the problem lives. Okay, so another component is, you may name it the core of the hypervisor. So it's a piece of code that actually handles the VM exits from the VM, do the necessary housekeeping, like allocating memory for the VM, etc., etc. And it's not very interesting, but again, one of the main functionality that it needs to provide is to provide some channels, some communication channels between the code running in the VM and the outside world. Again, so that VM can communicate and be useful. And again, this part, this hypervisor code, is not very large, even in mainline off-the-shelf products. Again, it doesn't do much, really. Majority of the code is really management code, right? That's not even under the control of the attacker. So again, there is not many issues with that part of the code, right? And also, it means that if you heard that, okay, my virtualization system uses hypervisor that is very small and it just passes messages, right? And it has been verified. Yay, that's great. But again, what other parts of the virtualization system are relevant, are security critical, and has not been verified, right? So that's a question to ask. Again, if you just verify this single piece of software, that's not the end of the story, right? Okay, so what else? If we want to run in this VM something looking like a normal operating system, so Windows or Linux or whatever, it will expect it can talk to hardware, right? So it can write to PCI config access space, it can write to IO ports, etc., etc. So the job of the hypervisor is to make an illusion that this operation actually works, and then that they act on some sort of hardware. So that's the job of the device emulator. So the hypervisor is responsible for intercepting all these actions by the device driver running in the VM and informing the device emulator, okay, the network card driver in the VM tries to send a packet, right? And device emulator does this job on the behalf of the VM. And this is a more problematic part. There are issues with that code because this code is relatively large, right? Again, modern hardware is relatively complex, right? It has, hundreds of registers that you need to emulate in order for the VM to be able to use it. And again, it creates some complexity that inevitably translates into vulnerabilities. Yeah. So this is the really problematic part that you should be aware of. And On top of that, a lot of virtualization vendors try to provide some additional services to the VM. So once you have a device emulator running, you do not need anything else to actually boot the VM and use it, right? But for functionality and ease of use, a lot of vendors provide some additional services. So again, there is some code running outside of the VM, so it's security critical from our point of view. There is a communication channel with some pseudo driver in the VM, and this code listens for requests. And the typical example is, for instance, shared folders functionality, right? It's very useful to have some fragment of the file system on the host be available directly to the VM, right? Very useful functionality. But again, it immediately creates an attack surface. And again, this part also tends to be large. It also tends to be not so carefully written, right? Because, okay, when you write a hypervisor, you have to be, very well skilled, etc. But, for running some crappy code running on the host, anyone can do it. And that creates problems. Okay, and finally, there is another functionality that is potentially dangerous, namely for many reasons. First of all, performance, but also security. You could give the VM direct control of a real piece of hardware. So allow this VM code command real PCI device, not some emulated virtual ones, but really give it access to the actual registers of the PCI device. And that creates a problems. One obvious problem is that PCI device can access host memory as well, right? Using DMA, direct memory access. So if you assign a PCI device to a potentially untrusted VM that can be malicious, then you need to make sure that it cannot instruct this device to do DMA, for instance, to override hypervisor body. And there is another technology named VTD that you need to enable to actually use it. Okay, so maybe some obvious summaries. So if the goal of the virtualization system is to maximize features, make it really friendly for the user, right? Make it really usable, then the attack surface grows because you increase the code base, you increase the number of APIs that must be handled by the security relevant code, and that's almost inexorably results in vulnerabilities. But that does need to be the problem, right? If the goal is features, and if you do not expect your VMs to be malicious, right? You use VMs just, to make computation easier or whatever. Then you don't expect that it will run malware. So you don't need to worry about security, and you can use that kind of hypervisor. But on the other hand, if the reason why you're using virtualization is to provide security by isolation, you want to be able to just isolate potentially compromised code in some cave and not let it interact with the rest of the system freely. Then it becomes the critical part, right? Then you must be careful when designing or choosing the hypervisor to see how these features are implemented, right? Or whether you have control on what amount of attack surface you expose. Okay, so the summary is hypervisors have non-zero attack surface, right? There are real-life vulnerabilities in it, really. So what's the conclusion? We should just abandon it for any security purposes, right? If they are so unsecure. The answer is not that straightforward because what are the other options? What other technologies can we use for isolating malicious code? And isolation is a crucial technology because everyone has essentially given up on writing the code that has no vulnerabilities. It's secure and works as expected. Especially if you talk about large applications like browsers, document editors, then it's totally hopeless. And yesterday you could listen to a talk. Guys showed that they wrote a single fuzzer that has found 100 vulnerabilities in IE. So it's really, really sad. So what's the current trend nowadays in the industry is that you have to isolate. In case of an application, you just try to isolate a large portion of the code. the one, for instance, does HTML parsing, etc., and run it in some sort of sandbox. And usually the sandbox is implemented by using the operating system facilities, right? So you think about solutions like Chrome Sandbox or Adobe Reader Sandbox, they just select some portion of the code, wrap it in some sort of sandbox based on an OS, and that's intended to limit the attack surface. Okay, that's good. If you remember how the word for exploitation looked in 2009 or 2010, then Adobe Reader was a primary target. There were exploits for it released like every 2 weeks, right? And after they used this separation, introduced the sandbox, it essentially dropped to 0. So that's very nice. The problem with this approach is that technology of sandboxing based on the operating system facilities is prone to exploitation via kernel vulnerabilities, right? Because again, even if you run in a sandbox, but if you can launch a kernel exploit and get execution in the context of the kernel, you can do anything you want. And the problem with this is, at least on Windows, the kernel attack surface is huge, right? And we're mostly interested in Windows. So you have 400 system calls, 800 Win32 cases system calls, and other things like driver IOCTLs or WDDM escapes to graphic drivers. So that is really huge attack surface, and the obvious result is that, for instance, the previous year there was 76 different CV items allocated for problems in Windows kernel mode. So that's really huge attack surface, and the problems happen, right? And this is not theoretical, because if you look at the contests like Pawn to Own or similar, you really see that's exactly the way how guys are able to break all the security of the browser. First, they get code execution in the sandbox, and then they use kernel exploit to break out of it. So that's really a problem. Okay, so it would be nice if you could compare in some quantitative way the isolation implemented by the well-written hypervisor, right, and say kernel of the operating system. And it's difficult to do in a really convincing way, because these are two totally different pieces of software, right? Again, presenting different APIs, so it's difficult. What people are very fond of doing is just measure the total line of code, or trusted computing base for that matter, and see if this product has a lot of lines of code, then of course it's less secure. And this reasoning is almost entirely useless, right? That's really sad. The reason is that the total line of the code does not tell you what percentage of the lines of code are actually devoted to treat the untrusted input, to deal with an attacker, right? And which are relatively harmless because they are just for bookkeeping or management purposes. So that's really comparing lines of code or TCBs doesn't tell you almost anything about security of the system. If you really need the numbers, if you must hear some numbers, so if you take Xen 440, so the recent one, it has about 1.7 million lines of code. So quite a lot. Again, the point is that it's mostly bloat. For instance, it includes a lot of drivers for virtual devices, which nobody would use. So you can strip it like by factor of about 10, right? To 110 kilos line of code of user mode code and 60,000 lines of code in ring 0, and still have functionality sufficient to run VMs in a useful manner. And if you compare it with Windows 7 kernel, it is believed to have around 2 million lines of code, and likely Win32K driver is larger, then you can see that there is a huge gap, right? At least factor of 10. But again, this comparison is almost useless again. And in fact, the difference in attack surface is even larger. Okay, so again, what it means is that if you want to hear some really meaningful comparison between these two, you just need to rely on someone's experience, right? For someone who is well aware how actually these two solutions work and knows the history of the vulnerabilities in these two products. And again, most agree that, again, the attack surface of a well-written hypervisor is significantly smaller than, say, Windows kernel. And for instance, you can look at the papers for the Microsoft Drawbridge project, and they explain really in a diligent way why they use a hypervisor to provide isolation. So that's nice. There are also some hard facts that are easy to back with facts, right? So the VM exit boundary, so the boundary between the VM and the hypervisor, is much stronger than the syscall boundary, so the boundary between the user mode and the operating system kernel. And the main issue is that in case of kernel user mode boundary, you have essentially the same address space, right? Some fragments of the address space are reserved for the hypervisor, but still you have the same page tables, the same address space. And that creates a lot of problems, right? So how normally a kernel exploit work is that an attacker can prepare some data structures in user mode and trick kernel into believing that it's actually kernel mode structures, right? And that creates a problem, like null pointer the referencing the kernel are a primary example. Again, the problem is that the address space is the same. Similarly, if you consider breaking out of operating system sandbox, so once you have code execution in, for instance, Chrome sandbox, then you know what is the basis of the libraries. You know the virtual memory layout. And the problem is that in the processes running outside of the sandbox, the libraries have the same base, right? Because they run on the same system. So again, some important piece of information are the same in the sandbox as outside of the sandbox. So that's another problem. Another thing is that at least until recently, the Windows kernel just handed the information about the memory layout for an attacker for free. So there was an API that an attacker could use. Dear kernel, what's the base of the kernel currently? And it would hand it for free. It got better recently, but only on Windows 8.1 and only for untrusted processes. But there will be more problems with this kernel ASLR on Windows. Finally, if you think about exploiting browser vulnerabilities, the reason why they are so effectively and reliably exploited is, again, because an attacker has a lot of control over the memory layout in the browser. Mostly because it can use JavaScript, and it can do things like heap feng shui, so allocate some heap blocks that will be aligned in a proper way, and that creates the memory layout required for the exploitation. So it sounds almost like a joke, but the hypervisors are inherently more secure than, for instance, browsers, because they do not have JavaScript interpreter in it, right? Again, sounds funny, but that's actually true. And again, if you look at the hypervisor, you don't have that kinds of the problems, right? You have a different address space. That for one. So what you need to get a real exploit, memory corruption-based exploit against a hypervisor, is you need two primitives. The first one is information leak from the hypervisor, so that you know essentially what the memory layout, and then some write primitive to get the code execution. And most of the exploits against hypervisors that I have seen do not work this way. They use on some shortcuts, like ASLR is not functional. For instance, the user mode binary of the hypervisor has not been compiled with proper flags, right? And then exploitation is easy. Or there are DLLs that are non-ASLR compatible. Then again, exploitation is easy. And again, almost all the exploits against virtualization software that I have seen work this way, which essentially say that if the vendor neglected to use this basic, 101 security practices, then it doesn't care much about security. There is one example of an exploit which is different, and I'm talking about Cloudburst exploit. So it was a vulnerability in VMware discussed in Black Hat USA 2009. And this is different. This time, the underlying vulnerability was so horrible that it allowed an attacker full read-write access to the address space of the device model. And then this capability is such powerful that you can write very reliable exploit even cross-platform. Okay. So there is one important point that normally you do not have to choose between the security or isolation implemented by the operating system or the virtualization. The reason is the beauty of the virtualization is that you can just stack it on top of the existing operating system, right? So you can do things like that. So this diagram shows how Chrome Sandbox works, right? You have the broker and the sandbox, and you can continue to use it, but just wrap all of it in a VM, right? So the idea is that with this setup, an attacker would have to first break out for the Chrome Sandbox, and then would have to break out from the VM Sandbox, right? So combine two solutions. And again, the beauty of the virtualization is that you can do it more or less easily, right? You can just pull the VM layer on top of an existing security solutions. And that's really nice. It's pure gain, but there are some assumptions. So first of all, you have to assume that the hypervisor can be attacked from the VM only once the attacker in the VM has root privileges, right? Because if the hypervisor can be attacked from within the sandbox, it increases the attack surface, right? So that would be wrong. And that assumption holds for majority of the problems. VMware is, I think, the only exception that exposes some hypervisor functionality to unprivileged user mode. Then you have to assume that there is nothing valuable in a VM, right? Because if after compromising this OS sandbox, attacker gets everything he wants, for instance, access to the internal network, then there is no reason to escalate privileges further, right? So in that case, wrapping in a VM does not help you. And then finally, you have to assume that the presence of the kernel drivers installed by the hypervisor in the VM, that they do not weaken the security posture of the kernel in a significant way. Because if, again, this code running in the Chrome sandbox can talk to the device driver installed in a VM by the hypervisor and use it to break out of the sandbox, and then it's bad. Okay, so these are non-trivial assumptions, but actually they are most of the time true. And then, again, just layering VM on top of all of this is really a good idea. So to summarize it, really isolation by virtualization can improve security, even if the off-the-shelf products that have a lot of problems, etc. Again, in order to maximize security, hypervisor-related code should be small, right? To make the attack surface as small as possible. And then the good thing is that it's possible to design the hypervisor in a way that can provide sensible functionality without sacrificing security. And I will try to show you examples later. Okay, so now we'll have a couple of examples of past and not so very distant vulnerabilities, just to illustrate what the attack surface, right? Okay, so the first case is really not that interesting, but it is very recent, right? It's Xen Security Advisory 108 that was released like 2 weeks ago. And it's received a lot of media hype because there was prediction that it's a very critical bug that would allow you really to fully compromise cloud providers. In fact, it's not that critical. What happens is that VM can trigger read beyond the buffer in the hypervisor space. So if you look at the diff, it's a very simple bug. You simply use a wrong constant in some range check, right? So that's really a very simple thing. Again, the impact is that some data leak from the hypervisor memory, or you can crash the hypervisor if you access the man-mapped memory. So again, not very interesting. I will show you more severe examples later. Again, it received, in my opinion, unjustified amount of interest from the media. Okay, so another thing is 4 relatively new vulnerabilities in Oracle VirtualBox that I have found and reported to the Oracle in March 2014. So they were fixed in 2014 July CPU, so just before the Black Hat USA when this presentation was delivered for the first time. And they are not that critical or that horrible, but they are interesting in a way that they are relatively new, but also they show you the common errors or mistake or design problems that can be done by the virtualization software vendor. Okay, these VirtualBox vulnerabilities are most related to the shared folder functionality. So just to reiterate how it works. So you have a VM. That VM has some communication channel to the VBox SDL process. That runs on the host, so outside of the VM. And the purpose of this communication channel is to give this VM access to some fragment of the file system of the host. So the protocol here is that VM can send, please read some path name for me, and then this VBox SDL process does exactly that. Accesses the file that's under the shared folder's root and returns the result to the VM. The problem with this code is that it's unfortunately too large. For instance, it supports both UTF-8 and Unicode path names. So this path name here, request path name, can be both UTF-8 or Unicode, right? And the guest can select which one encoding likes. And it does not check null termination early, maybe because it's difficult to tell whether a path name is null terminated if you don't know if it's UTF-8 or Unicode, right? Also, this code needs to do casing corrections, right? So if your VM is Windows, that usually does not care on the casing of the path names, but the host is Linux that distinguishes the path names of different casing, then you have to adjust casing in some cases. And again, all of it is done in the hypervisor. Then finally, guest can specify path delimiter. So instead of separating path components with slash, you can say there's an arbitrary character and dear hypervisor, please use it as a path separator. Again, that's simply too much if you just look at it. And the first problem is memory corruption in a function that builds the full path. So essentially what it does, it tries to do this path delimiter corrections, right? So you have some buffer that comes from the VM, and again, it's not null terminated. That's an issue. And what this code does is just scans for each occurrence of the character specified by the VM and changes it to the path delimiter, changes it to the slash. And does it until it sees terminating null. And again, because there is no null termination, again, VM can send the string that is not null terminated, it means that the hypervisor will overwrite memory after the buffer, right? So again, memory corruption. This is a very limited memory corruption, and I don't know how to actually exploit it in case of VBox. It doesn't mean it's impossible. Again, in comparison, if such a vulnerability was in a browser code, its exploitation would be really routine, right? The usual trick is that you massage the heap so that after the input buffer that is then attack vector, you store some JavaScript array objects, right? And array objects is interesting because if you overwrite only one byte in it, namely the size field, then it gives you a lot of capabilities because you can write and read beyond the end of the array. And then it's essentially game over. You have read-write access to all the address space. Okay, so the lesson. The host service code should accept only narrow input, right? And all the conversions, normalization should be done in the guest if possible. Okay, another one is new vulnerabilities shared for the directory traversal. Again, if you receive the path name, you should be aware that it can contain things like double dot components, right? So you cannot just blindly concatenate it to the shared folder's root because you get directory traversal immediately. So you need some way of sanitizing input, and how VBox does it is, again, a little bit too complicated. So essentially, you count the number of double dot components in the path name, and you count the number of normal path names, of normal components. And if the number of the normal path name components is greater than the double dots, you allow it, because there is no traversal. Such a path would be rejected because you have too many double dot components. And again, it's a bit too complicated, right? And interestingly, the problem is here, that this code treats both backslash and slash as the path separator. And it's okay on Windows, because on Windows, both slash and backslash is the path separator, but it's not okay on POSIX host, for instance on Linux. Because on Linux, backslash is not a path separator. So what you can do is create such a directory in a shared folder. So this part is actually a single directory, right? Not nine directories. And then if you access that path name, VBox will allow it, right? Because it will think that you have 9 normal path components here and then 9 double dot components here, so no problem. But in fact, this is a single directory, right? And that second double dot will traverse past the shared folder. Okay, the lesson same as before. This sanitization should be simple, really, to not make too many errors in it. For instance, you could just check for an occurrence of a single double dot and then immediately reject it. It will be enough, right? And you have some OS-specific tricks that you can use. And again, just beware, portable code is sometimes very difficult to write in a secure way. Okay, the third one is a data leak. It's not that important, so let's skip it since I'm running a bit late. The fourth one is even more funny. So it's not something that can be triggered by the VM, but it's an escalation of privilege on the host. So if there is VirtualBox installed on the system, unprivileged user mode code can escalate to the kernel. And how it works, VBox has 2 components, one in user mode and another a driver in the kernel. And they need to communicate between themselves. And the way how VBox engineers arranged it in this case was very efficient, shared memory. So you have some location in user mode address space that is mapped to the same memory as some location in the kernel in the VMM R0, that's its driver. And that would be fine. That's not a problem in itself. The problem is that the kernel component trusts this struct VM here without any limit. Particularly in this structure, there are pointers to the kernel procedures. And again, this driver just blindly dereferences them. So it means that exploitation is simple. In this user mode process, you can just overwrite the location in this structure that holds the kernel mode pointer and wait for the kernel to dereference it, right? So obviously, just sharing memory with an untrusted user mode and trusting the contents of this memory is really fatal design flaw. Okay, so these are the VBox vulnerabilities. Again, I hope they are instructive. There's another one in early version of Xen. So CV 2007-5497. So this time it was integer overflow in some component of Xen that ran in privileged DOM0. And again, it was parsing a large data structure from the VM. This time it was file system. Again, it's a flaw in itself that such a complex data structure is parsed by something in the host. And the solution is do exactly the same thing, but just move all this code to the VM. Just parse the file system in the VM. And then again, the same vulnerability existed, but it has no impact, right? Because if all you could do was to get code execution within the VM. So again, the lesson, this technology to offload to VM as much as possible is very powerful and can really make a difference. Okay, so another vulnerability, this time in KVM a couple of years ago, there was a talk at Black Hat as well. So this time the bug was in the code implementing emulation of PCI hot plugging. And VM could trigger it by writing to emulated chipset registers. Again, a nasty bug, and you could think, do we have any generic mitigation against that kind of vulnerabilities? For instance, could we just deny all PCI config access to the VMs? And the answer is no, because PCI config access is what VM uses during its boot to configure the virtual hardware. But the point is that it's needed only during the boot time. So you could use the technology named delusional boot, in which you start the VM with unrestricted config. So for instance, it can use all the PCI config access space, let it boot, then in the runtime change the config. So you can save VM, change the config to the more restrictive one, and then restore VM. And then the point is that only after then you expose the VM to malicious input. So for instance, open a browser in it. And because once the malicious input reaches the VM, then you no longer have this functionality exposed, then you cannot use it for exploitation. So I guess that's a pretty nice trick. Again, all these technologies that I will show you are actually implemented somewhere. So it's not science fiction academic projects, right? It's really used in production. Another problem again, is in device emulator. So you have CV 2012-29 vulnerability, and it was heap-based buffer overflow again in QEMU, in network card emulation. And again, as I mentioned, device emulation is really source of the problems. So what you can do, you can use this nice vehicle for providing isolation, which is a hypervisor, to just isolate a device emulator. So no longer run device emulator in some privileged environment, like on the host, but in a separate dedicated VM. And then even if malicious VM can exploit some vulnerability in it, it gets code execution in a restricted environment, which is pretty nice. What else? Again, in fact, the best thing to do is to just get rid of the device emulator entirely. If you can load special drivers in the VM, so in essence, you tell to VM that please don't expect real hardware or virtual hardware. Please use a special driver that just expects the functionality exposed by the hypervisor. So talk to the PV driver, not to emulated driver. Then you don't have this device emulation at all. And again, it's just significantly decreases the attack surface. Another one, CV 2007-69. So it was vulnerability in Windows kernel in networking code, particularly for the IGMP packets processing, and it was pretty devastating. You could get remote code execution in the Windows kernel. So if not everyone is asleep, then you should realize it's a vulnerability in the Windows, not in the hypervisor, right? So why do I mention it here? The point is that you can use, again, isolation implemented by the hypervisor to help with that kind of the problems. So the idea is to use so-called service VMs. What you do is you create a special VM, dedicated VM, and you move some privileged code, like drivers for the network card, or the whole networking stack, DHCP client, etc., etc. So a lot of some functionality from the host, and you move it to the dedicated VM. So, in order to make it actually work, you have to give this VM the access to the physical device, so to the network card, for instance. So if we go back here, so the service VM would live here again, but you won't need this communication to the host, right? It would be more or less self-contained. Again, you get some portions of the host kernel and move it to VM. And again, if there is any vulnerability, for instance, in the networking stack or the VLAN driver, what an attacker gets is not immediate root in the kernel, in the host operating system, but in the VM. And that's nice, and projects like CubesOS or XenClient-XT do it by default. So they create the network VM by default to limit the impact of an exploitation of networking code. Okay, and finally, the project that's not finalized yet is an idea that you can make the whole host of the Type 2 hypervisor a giant service VM. So just normally you think that the host is privileged and it can do whatever it wishes with the VMs, right? And this technique just inverts these solutions. This time the host is just a bag for hardware, essentially. And it's deprivileged, so it cannot mess with the VMs. So I'm running a bit late, so if you're interested, so just look at the white paper. Again, it's something for the future, but if it works, it would be pretty interesting. Okay, and finally, deep safe. My favorite deep safe. As I mentioned, deep safe is a virtualization solution which is totally different from the above. Again, it was created with security in mind. The idea why it was created was to increase security of the Windows operating system. And how it works very similar to the Joanna Rutkowska Blue Pill projects. Hopefully some of you remember Blue Pill from 2006. So what happens is that Windows operating system starts normally, and then at an early phase, it loads the kernel driver, the deep safe driver, right? And what this kernel driver does, it installs itself as a hypervisor, and then deprivileges the Windows operating system to run in a VM. So from this point, Windows does not run on the bare hardware. It does not control the hardware or CPU. It runs in the VM, right? So it's exactly what Blue Pill used to do, but this time the purpose is not to achieve rootkit functionality, but have some level of control over the operating system. Because again, from once the DeepSafe driver is loaded, then Windows operating system is not all powerful. There is some layer of code which is more powerful, namely Hypervisor, and it can control what Windows does. And why take all these difficult steps? Again, the reason is for security, because a lot of security solutions that reside in the Windows kernel, like antiviruses or HIPs, have a problem with kernel exploits, right? Because if an attacker gets code execution in the kernel, so it gets to run in the same privilege level as other kernel drivers, it can disable them or can erase them, do anything it wants with them. The problem is that normally Windows kernel is the most privileged part of the system, and once you get code, your exploit run in this most privileged part, you can do whatever you wish. And DeepSafe tries to change the situation, again, because it installs itself as a hypervisor, and theoretically, Windows cannot attack the hypervisor, right? That's the idea. So that's very nice, and again, the purpose of the DeepSafe is to monitor the execution of the Windows kernel and just try to spot if rootkit is trying to install. Because sometimes rootkit performs actions that are easy to spot from the hypervisor level. Okay, so that's nice, and does it work, essentially? So indeed, when CPU is running in the context of the VM, so running Windows that used to run on the host, but now it runs in the VM, DeepSafe configures extended page tables so that CPU cannot access memory of the hypervisor. That's nice. That's how it's supposed to work, right? Again, that shows that you can use the hypervisor technology as good, effective method of isolation. But how about PCI devices, right? I already mentioned previously that PCI device can use DMA to the memory. And in this design, VM has all the control over PCI devices, right? So in order for Windows to not notice that it runs in a VM, it still must be able to talk to the network card, to the graphics driver, etc. And again, I mentioned that you need VTD to prevent PCI devices from corrupting your hypervisor memory. So how it works is that, okay, you have some virtual machine, okay, you give it ability to configure the device, but there is additional layer here. It's called DMA remapping hardware, and it checks all DMA accesses done by this device. And if this DMA access goes to the memory allocated for virtual machine, that's fine, it's allowed. But if it sees that you try to corrupt hypervisor memory, then it's denied. So again, it means that in order to be secure, DeepSafe must configure VTD, right? And does DeepSafe use VTD? And the answer is no, unfortunately. At least in the tested version 1.60, so the latest available. And again, this knowledge is not something entirely new, right? Particular DMA attacks against Xen hypervisor was demonstrated by me at Black Hat 2008, so a long time ago. And also Joanna has written an entry in her blog just explaining that okay, preventing DMA attacks is, it's a necessity. You have to do it in order to be secure. They do not do it. It's not officially known why. They said when I talked to them that it's planned in the future releases. Unofficially, they told me that it's simply difficult to use VTD on broad variety of client systems because a lot of machines have broken BIOSes, and it's difficult to configure VTD on that machines, and that cause a lot of crashes, etc. So that's the reason why they do not enable. Okay, so the impact is that you can compromise DeepSafe integrity. So if an attacker gets control over your Windows operating system because you open a browser, then browser got exploited, then a kernel exploit was loaded, then you can launch another step and attack the DeepSafe hypervisor. Again, doing this arbitrary DMA is not very complicated. So essentially, you don't have to configure PCI device yourself. You can use existing drivers already loaded by the Windows. So the key point is to open a file with this particular flag, flag no buffering. And it tells operating system to do exactly what we need, to do DMA to the user buffer. And then you have two options. Either you have to cheat operating system and say that, okay, this is my user mode buffer, but it's actually at physical address P. So you corrupt the data structures used by the kernel to translate from user addresses to the physical addresses, right? So you just overwrite page tables. And then if you just issue the read file or write file, the kernel will configure properly the hardware, and it will do DMA to the physical address P of an attacker choosing. One point is that it doesn't work with BitLocker, because with BitLocker you cannot essentially do immediate DMA from the disk contents to the user mode buffer. You have to encrypt or decrypt first, right? But normally it works without BitLocker. Okay, so what can we do with that functionality? Again, it means that we can get total control over the deep safe hypervisor. So essentially we could disable it if we can just knock out the proper routines. But that's not a sensible thing to do from an attacker point of view. Just think of it. So you can control the hypervisor, right? Hypervisor is a nicely isolated piece of code that has full control over your operating system. And again, the rest of the operating system cannot, well, see what happens with the hypervisor. So in fact, it's a perfect place for a rootkit, right? If you place a rootkit there, you have excellent control, and you are protected from, say, antiviruses running in the Windows host. And for a proof of concept, I did exactly that. I have injected a very simple rootkit into the deep safe hypervisor. What it allowed me to do was to full patchguard in Windows. So as you remember, patchguard in Windows periodically checks if for the signs of rootkit in the Windows operating system. And if I control the hypervisor, I can full patchguard, right? I can tell you, no, there was no changes done to the crucial operating system data structure, so don't worry. Again, I can do it because the hypervisor runs as a more privileged code than the VM, right? So whenever the patchguard tries to, for instance, read model-specific register to see if it changed, hypervisor intercepts this operation and just feeds it the wrong value, right? And again, the effect is I can disable all the patchguard functionality running in the VM without even touching the VM memory. So that's a very short demonstration how it looks. I don't know how to make good demonstration. Just a matter of running a simple exe and seeing that it works. So, but what happens here is that first you find the location of deep safe in physical address space, then you overwrite it, and then again you can run a backdoor that gets full control over the Windows VM without Windows VM noticing it at all. Again, you can see that some system calls return magic values. It means Windows kernel is totally compromised, but again, patchguard doesn't see anything, and the deep safe does not see anything. Okay, so there are more deep safe concerns, but they are not entirely related to the hypervisor topic, so let's skip it. It's already late. So just a short summary. So hypervisor have no negligible attack surface, right? There are problems with them. But still, despite the above, they are useful to protect even less secure operating system, right? If you had very secure operating system, you would not need a hypervisor to protect them. It's the other way around. And also, there are generic methods to reduce attack surface of the hypervisor that you can actually use in deployed software to reduce attack surface, and they really make a difference, right? So if you design a hypervisor, be aware of that. If you choose a hypervisor for yourself, try to find out what methods the vendor applied to really make the hypervisor as secure as possible. Okay, that's all for today. Okay, it's late, so I will evacuate and take questions outside. Okay?